What about effort level?
It is the most intensive thing I've ever done in my life.
Hi everyone, I'm Jon with Radenso.
I'm Rob with Radenso.
And thanks for joining us for part 3 of our DSP video series. So for the first couple of videos, if you haven't seen them, make sure to go back and check them out because that kind of lays the fundamentals for some of what we're going to talk about today. But we kind of covered what is digital signal processing and some of the basic operations that we do. So now that we understand what DSP is and why it can benefit your radar detector, now comes the tricky part. From our standpoint, we have to figure out how to actually implement it.
Right.
Like, how do you do your DSP in hardware?
Yeah.
And it's complicated, right?
Yeah,
I mean,
we know why it's good, but how do you actually do it and where?
Yeah.
Right.
So that was one of the questions that I kind of first asked Rob when we were designing this thing. I mean, you've seen our digitizer before, which obviously has an FPGA on it, but why did we choose that? Well, there's really only 2 popular ways to do digital signal processing nowadays, and that's with either a standalone specialized DSP processor, like a Blackfin, or by kind of rolling your own with an FPGA. You've got these DSP processors that are designed, but the thing with a general purpose DSP is that it's not designed for Rob's DSP versus Jon's DSP versus escorts or whatever. It's designed to be able to handle a lot of different generic DSP tasks. Now, I'm not saying they're bad. They're pretty fast.
They're actually pretty amazing chips.
Yeah. But we'll talk a little bit about that later. Now, as far as the FPGA goes, when you get an FPGA, it doesn't do anything. That was really surprising to me. And it's like when you buy a Blackfin or a DSP processor off the shelf, it comes with this neat instruction manual. It tells you exactly how to program it, how to talk to it to get a certain type of operation.
Right, it's got parts that are inside.
It is a processor.
Yeah, it's a processor, and processors run instructions. And you can look at the manual for any analog devices or TI DSP, and in the manual there's a list of instructions that processor can run. The parts are all wired together statically, but you can run instructions on it and tell it what instructions you want it to do to whatever data you have.
Yeah. Now, I know this sounds crazy, but an FPGA is not a processor. I really think we need to make sure that we're drawing a distinction between a processor like an Intel, like a Blackfin, even a GPU in some ways. Those all run instructions, as Rob said. An FPGA is not a processor. It's just this thing that doesn't do anything until you tell it to how to connect and how to operate. You can poke it with a stick and it won't do anything.
It's basically a chip with a box of parts inside, but they're not necessarily soldered together. So when you first turn on an FPGA, it just sits there because it's got millions of parts inside, but they're not actually connected until you tell it how you want it to, what kind of chip you want it to be.
Yeah. So when it came time for us to decide which direction to go with our hardware for Theia, our choice was between a really powerful, really easy to use, well-documented general purpose DSP processor like a Blackfin, or this chip that is totally useless until you figure out how to utilize it correctly.
Right.
So that sounds like a no-brainer, but we chose the totally useless chip. And we're going to get into why we chose that next. It's actually pretty incredible. And for me, learning about this has been one of the most fascinating parts of this entire process. It's just that humanity could even figure out how to create these things.
Right, they're pretty incredible parts.
Yeah.
And then trying to figure them out is a very incredible task.
Yeah. Great, so let's take a look. Okay, so before we talk about what is inside this box, this chip that is essentially a box of parts, I want to talk a little bit about where else FPGAs are found. So I wasn't super familiar with them outside of the radar detector space. The Max 360C has one, which is kind of where I became familiar with them. But Rob taught me that they're used all over the place, wherever really high-speed communications or signal processing is happening.
Right. You see a lot of these in communications. So a lot of equipment that's in maybe cell phone towers would be using these. They're used in all sorts of signal processing spaces. So you might find them inside of like maybe a really high-end audio equipment. They're used in places where being able to reconfigure something is very important without redesigning the entire board.
They use them like aerospace or even on like space missions and stuff?
Yeah, you bet. You'll see FPGA designs in a lot of cutting edge places. An FPGA is used in a lot of these places where if there were more of these devices being made, maybe they'd make a chip that did something very, very specific, but no processor would ever fit the bill. That's kind of where FPGAs rule, is where there needs to be something incredibly customized, but in order to be able to make a chip that did that very customized task, you'd have to make tens of millions of them.
Interesting. So you've got a bunch of different FPGA devices here on the table. I mean, are these I know some of them are your development tools, and,
right.
and others are actually commercial products, which we've purchased, like the software-defined radio here.
Sure. Yeah, these are a few examples of FPGA development boards that are made by a few of the different people who make FPGA chips. The biggest ones obviously are Xilinx and Altera, which is now Intel, and Lattice Semiconductor.
And by the way, just so people know, those two brands that Rob said are both used in radar detectors. Escort and us use Xilinx.
Correct.
And I believe Valentine chose Altera. He's
There's the
using it
Max 10
in a little bit of a different way than Escort and we do. But yeah, these companies, the same ones, are making these chips for everybody.
Right, and these things go from the incredibly small, incredibly inexpensive, to parts that have thousands of pins on the chips and cost $25,000 for one chip.
So you're telling me one FPGA could cost $25,000?
Absolutely.
That's crazy.
Right.
Wow. All right, so let's just get into it then.
Okay.
I think the name of an FPGA, what it stands for, says a lot about what it actually is. It stands for Field Programmable Gate Array. Right. And the important thing to think about there is that it's field programmable, which means it doesn't have to be designed it doesn't have to be shipped back to the mothership every time you need to make an update to actually change the hardware. And the gate array is the parts that connect together and actually make it do what it does.
Right, there's a big array of logic gates inside that you connect the way you want.
So with FPGAs, I said earlier that it's not a processor, and that sounds like such a bizarre concept because it looks like a processor. I mean, it looks like a black IC, right? But what's so special about them is that it allows us to actually change hardware with software.
Right.
That sounds impossible. I really didn't understand it at first because hardware with stuff like this is hardware to me. It's something I can hold in my hand and I can see the circuits and the capacitors and how they connect. Right. I didn't understand how you could create that with programming language. That just seems so bizarre.
Well, if you think about it like this, these are all pieces of hardware, but they're connected by these traces, by the wires on the board. Those are what we get to change when we program the FPGAs. Maybe the parts are all still static, but we get to change what wire goes where and what parts are hooked up together.
So to help you visualize how this is possible, we put together a couple of graphics. And the first one that we're going to look at is this one here, which shows kind of a grid of orange blocks within the FPGA. Right. And each one of these orange blocks is the fundamental unit of an FPGA, and it's called a CLB, or a configurable logic block, or a logic cell, sometimes people call them. And for me to understand how an FPGA worked, it was critical for me to understand that each one of these blocks is a microscopic collection of circuits that is etched into silicon, essentially. Right. And all of them are identical. So you have tens of thousands of identical circuits etched, that basically in an array that fills up this device. And all of those are technically capable, they're physically capable of being connected to each other. However, when the FPGA comes to you out of the box, it's almost like there's a roadblock in between each one of those logic blocks that prevents them from talking to each other. Right. Which is why it doesn't do anything at first. Sure. So what's crazy about them is the programming language, which is called an HDL, or a hardware description language, I think, right? Is designed totally differently than like a C++ or traditional language would be. An HDL tells which roadblocks to remove from which CLBs and
right.
how
So
they
it's
should talk to each other.
being a hardware description language, right? When you program, you're describing with your code how you want that hardware to act. And the job of the synthesis tool, which is the kind of equivalent to the compiler you use in programming, is to take the hardware description that you write and figure out how to connect those CLBs together to make the hardware that you've described.
So it just seems like such a crazy concept, right? So you can take a circuit, let's just say that you have let's say that you have an analog filter in here. You can connect these logic blocks in a way that performs that exact same filtering function.
Right. What's really interesting about these FPGAs is we have these CLBs that you talked about, this huge amount of general purpose logic, but then we have inside of that a bunch of things called DSP slices, which are very specialized pieces of logic. They're still not connected to anything, but they are built that they can be connected to do math really, really quickly. And so if we wanted to do something that was mathematically intensive, like a filter, when we describe the way that filter is built with our HDL, we'll start connecting our CLBs to these DSP slices, and we'll synthesize that filter we described by connecting those resources.
It's kind of crazy because since these blocks can be connected in any way, you could have, which we'll show on the screen here, this manner of connection. You can see it's kind of a very neat linear connection, and then this one, which looks a lot kind of crazier and all much more complex. It's the same FPGA, but they perform completely different functions. It's different hardware because we programmed it differently. We're not changing how it behaves. We're changing the actual physical ways it connects. It's a different circuit.
Yeah. So using two different hardware description of the same chip, you will connect it to do fundamentally different things and be kind of connecting to fundamentally different circuits.
So here's something that's critical that I learned from Rob, and that's that one of the fundamental differences between an FPGA and a standard processor is that everything in an FPGA happens at the same time. And I'm not exaggerating, it's literally simultaneously. And to explain what I mean, we'll show this graphic on the screen. So the way that a standard processor works is that it has instructions fed to it to perform an operation. It does that operation, sends it out, great, and then goes on to the next operation that it's waiting for.
Yeah, when you program, you are putting together a list of instructions that operate one after another.
And it goes out, done, 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 done.
Yep.
And it has a queue, essentially.
Yeah, you have a program counter as part of a CPU. When you compile code, you are basically turning that list of code that you wrote into a list of instructions for the CPU to follow in order. Pull data from here, add it to this data from here, store the result here. All right, next instruction, right? And so things happen in this sequence, and that sequence operates as fast as the clock of the processor is running. So if you have a desktop that has a 3.6 gigahertz CPU frequency, you are advancing through these instructions at a rate of 3.6 billion per second. But you're only ever doing one instruction, say on a one-core CPU anyways, at a time.
Yeah.
And that's why multi-core CPUs are so important, because if you have an 8-core CPU, you can be doing 8 of these instructions every clock cycle.
So with an FPGA, we've already said that we can build circuits, literally build circuits inside our chip. What if we had an FPGA that had enough of these logic blocks where we could build multiple actual processors inside an FPGA? So again, I'm not saying that FPGA is a processor. I'm saying that we're going to connect these things in a way that's so complicated that we literally build multiple CPUs inside the FPGA. Is that possible?
It's what we're doing, because if you think about it, a CPU is just hardware, and we write in hardware description language. One of the things that we describe with our HDL is a CPU. So inside of this FPGA, we take some of these blocks, of which there are tens of thousands, and some of those blocks are used to describe a CPU, which runs inside of the FPGA. We just describe what a CPU hardware looks like and instantiate one.
So whereas a normal DSP processor has a queue of operations, let's just say it wants to add, subtract, multiply, divide, filter, whatever. Our FPGA inside of it can have one processor devoted to each of those tasks. And as the signal comes in, it can go to each of those processors at the exact same time.
Right. But they're not processors like a desktop processor. These things are
designed specifically.
These are blocks of logic that we've described as hardware that do one of these tasks instantaneously, right? So we have a CPU inside of it just to handle some basic housekeeping. It's basically,
which is our microblade.
Right, our microblade CPU. And all that thing's doing is answering the phones, basically, right? It's just doing a little bit of housekeeping and some very low level, none of the DSP. Then we have these little DSP CPUs, to be right, that basically are modules. They take little blocks of the CLBs that we have.
Let's throw this up on the screen and actually show you guys. So obviously this is not in the entirety of how we're using it. But just to get across the concept, you can see what Rob's talking about. So he built and designed inside of this several different blocks, which each operate concurrently. They're always churning away all.
Right, these guys aren't waiting for their turn for their instruction to run. They're running every clock cycle. These guys are doing their task, right?
So for example, like if you want to have an automatic gain control, something that makes sure that the gain is always optimal for the DSP that we're trying to do, you designed this block specifically to do that, and it's incredibly efficient at it because from the hardware level, it was designed just for this task, as opposed to using a more generic kind of Blackfin DSP or something like that.
Right. So basically, the way that we do the math for some of these detection circuits and some of these automatic gain control circuits, just the way the math worked out wouldn't have been very efficient on some of that hardware. It would have either used way more resources than it would have needed, or it would have been constrained by not having enough in some spots. And so with this, we get to make all those resources from scratch. So instead of saying we want to have, you know, some parts of this design that have to go through some piece of hardware that was already physically on the chip, we just designed the perfect hardware to solve that problem.
That's pretty crazy. That's really insane. I mean, the concept to me that we could have multiple specialized hardware circuits that we designed from the ground up inside one chip is just mind-blowing.
Right.
Now, humor me this. Let's say that we continue R&D in a year and a half down the road or 2 years down the road. You say, oh, wow, I figured out this crazy DSP algorithm, but the way that our hardware is set up inside the FPGA, we can't do that. I really wish that we had the hardware to do it. Well, with an FPGA, you literally just change the hardware with a firmware update.
Yeah, when you do a firmware update on something like this, you're not updating the code that a CPU runs. You're updating how the CPU is built and how all these DSP blocks that we built are connected and how many parts they use. When you update the software on an FPGA, you're completely rewiring the inside and reconnecting these blocks to do completely different jobs if you want to. So once you program it, you can program it any way you want, and it's as simple as...
That's just so future-proof. I mean, this is the kind of thing where it really, as long as you have enough room in the FPGA, as long as you didn't constrain yourself by having one that's too small at the beginning, which we made sure not to do, we bought a pretty big one, then that just leaves an incredible amount of room for in 4, 5, 6 years, you're fundamentally getting a new radar detector every single time we update the HDL on the FPGA.
Sure.
That's pretty wild.
Yeah, but that's the thing. When you talk about a software-defined radio, which we've been talking about a lot, the fundamental parts of this radio that would normally be hardware, filters, mixers, analog gain or automatic gain control, that's now defined in software. And when we update the software, we update the fundamental structure of how that radio is built. It's almost like shipping out a new circuit board every time we do a software update.
That's crazy. And then in terms of, kind of lastly, in terms of the efficiency, you talked about how they're built specifically to do one thing. One of the analogies that I like to think of for me is that, you know, if you have like an SUV, it's going to be pretty good at a lot of things. You know, you can maybe do a little off-roading, you can fit a lot of groceries in the back, you can maybe go pretty fast with it. But if you look at like a Ferrari or a Corvette, that's specifically designed to do one thing, right? And it's going to go fast. What's crazy about the FPGA is we can specifically put a Corvette for when we want to go fast here, SUV for when we want to tow stuff
Sure.
here. And we can actually have all these things concurrently working together to build the best radar detector.
Yeah.
And that's pretty awesome.
Yeah, I'm really happy with the selection of the FPGA. It's definitely something that takes a tremendous amount of energy to do, but when we look at how constrained we would have been if we did this the conventional way, doing this would border on impossible. There would just not be enough resources to do that job right.
Let me ask a obvious question. So we've just sat here for the last 20 minutes or whatever, waxing poetic about how amazing and life-changing these
Sure.
FPGAs are. Well, if that's true, why isn't everybody using one?
Well, it's a good question. Obviously, it sounds like it's a jack of all trades. I mean, amazing chip to use. And
Jack of all trades, master of all trades, right? Why wouldn't I
why
use it?
compromise? Well, the thing about one of the most attractive things, I guess a few of the most attractive things about a conventional TI or analog devices DSP chip is that the barrier to entry is very, very low. You can sit down almost anyone who's a pretty experienced programmer and have them program that hardware to do a job. They're inexpensive, they don't draw a lot of power. They're great devices because they're so easy to bring up quickly, and you can kind of copy and paste code and stuff like that. There's since it's a chip that there is one way to use it, it's pretty easy to get up to speed with one because you only have a few options of how you're going to do your job. With the FPGA, we are not constrained by having a few ways to do things, but the barrier to entry is much higher.
If I ask you to describe how difficult it is to get to the point that you're at, learning FPGAs, how difficult is it for you? How difficult has it been for you personally?
So I started doing FPGA design for fun a couple of years ago when I was overseas. And I never really understood it. I never spent enough time to really understand anything beyond making maybe an LED blink. To get to the point where we are now, where we're using highly efficient custom algorithms implemented in hardware design, it took maybe 2 or 3 years of trying to master this and tens of thousands of dollars in parts and software and licenses.
What about effort level?
It is the most intensive thing I've ever done in my life.
Really?
Yeah, I would. Well, from the engineering perspective.
Yeah.
I've done a lot of work in engineering, but really taking ownership of working DSP-based solutions and FPGAs and learning all the intricacies. I've been doing this for several years, and there's still plenty that I don't know. I think that to really go from not knowing anything about one of these to having mastery of it takes many years. A lot of people kind of...
and I guess a lot of those guys that do know it are probably working for Lockheed Martin or those huge defense or scientific corporations.
Right, a lot of these people...
Samsung, companies like that.
Yeah, a lot of this stuff you basically have to find someone to mentor you in, and then you basically grow into a specific company's culture of how they use FPGAs. And it's really trying to do it without the support of peers and mentors and factory representatives and stuff like that. The barrier entry is very, very hard. It takes a long time to learn how to do this the right way. You have to be very, very pedantic in the way you design the board to hold an FPGA. There's a huge amount to consider that you simply don't have to consider, but there's also a huge benefit if you make that investment.
Yeah. Well, I'm certainly glad that we found you, and I'm glad that we're doing this. It's been awesome for me to learn about FPGAs.
Likewise, I'm learning more about it every single day.
Truly blown away by them.
Yeah.
And I think what would be cool is while we will end the normal portion of the video here, because I know that this is already kind of a techie, abstract video. It's hard to follow, even for me, guys. I mean,
well, it's complicated to try to wrap it up into something that's really easy to make it bite-sized. It's tough. That's the hard part.
But if there's anyone out there who does want to learn more and actually see physically into the FPGA for Theia, what it looks like, what some of the connections look like, stay tuned after our little exit here, and we'll do kind of an unscripted just look at Theia's FPGA architecture with Rob. It's going to be super confusing. So
this is super nerdy.
Don't expect to understand it, but I even think visually it's amazing to see the level of complexity. Even if you don't understand anything on the screen, when you see how many gates there are and how many connections they all have, it honestly blows my mind. So stay tuned if you're interested in that. If not, really appreciate you guys sticking with us through this one. It's been great to have you as always. Make sure to like and subscribe, and we will see you next week.
Take care, guys.
So if you've made it this far and you still want to learn more about FPGAs, congratulations, you're a rare breed.
Yeah, definitely.
But honestly, this is the part where, for me, it started to make sense when I could see things visually, both in terms of how they worked, but also just being absolutely blown away by the sheer complexity of this. I mean, it blows my mind. So to explain what we're looking at here, on the center of your screen, center left side of your screen, this representation is actually Theia's FPGA design as it currently stands. This is the real deal. I mean, Rob, do you want to explain what we're looking at here?
Yeah, so this is...
the bird's eye view, zoomed out.
Yeah, so we're looking at the bird's eye view of two things. This one on the left is showing the actual logic elements that we talked about and all the other parts of the FPGA, and we're going to see how they're actually wired together when we basically start describing. Yeah, we describe hardware, and this is kind of the result of describing that hardware. We synthesize that into connections between those parts that we showed in the diagram earlier. In the right window here is the actual pins, the pads on the FPGA chip itself, and you can kind of see, we'll kind of take a look at what's connected to what pin. And
so those are the little BGAs kind of.
Correct. Yeah, these are the balls of the of the BGA array, and for instance, it's like one of the analog to digital converter connections, and we'll be able to follow this circuit all the way through and see what it does.
Cool. So if you zoom back out, the first thing that jumps out to me is there's a lot of blank space here. What's going on there? So like up where your mouse is there, we have not used that portion of the FPGA yet to describe any hardware.
When we talked about taking this thing out of the box and it not doing anything, when you take one of these out of the box, there's nothing connected. There's no wires. But if you zoom in, there are these CLBs.
Okay, so this is cool because in our video we talked about the CLBs, configurable logic blocks, being literally a collection of circuits that are programmable, that are etched into the silicon, but these are all identical, right?
Yeah, all the CLBs are identical, but on the FPGA, aside from the CLBs, there's a few very special pieces of logic that are also not connected to anything. For example, we have some of these DSPs.
So these DSPs and these CLBs, you've got thousands of the CLBs. What, 50,000 in this FPGA, I think?
Yeah, that's accurate, yeah.
And they don't do anything. You have to literally connect all of them. That's just crazy.
Yeah, well, I mean, everything...
But that's what you build things out of in an FPGA.
Right, when you describe this hardware, you want to have complete flexibility about what's connected to what to make the thing that you're describing. So you basically have a blank palette and these boxes of parts, and it's up to you to figure out how to wire them together. So
the empty looking ones are the DSPs, right? And the ones, the other identical ones are just grids of CLBs.
Yep, so and then over here we have a couple of other special devices. This is memory. These are 18-bit memories that are, we also have a bunch of them that are not doing anything. Instead of having a memory chip like a DDR inside, we also have small bits of memory that we can connect to make these things happen.
So what's the deal with those DSPs? Like,
so a DSP is very, very special logic that is incredibly fast at doing the kind of arithmetic that we need to run filters. When you talk about the performance of DSP, it's typically talked about in max per second, MAC, and that's a multiply accumulate, which sounds really weird. A multiply accumulate is basically a multiplication and an addition. And it's crazy to think about this, but 90% of the work that we're doing in DSP boils down to multiplication and addition. So
that's just a special logic element that's really good at that.
Right, and this is typically what you'll find in a DSP.
Like a Blackfin.
Correct, and they have a very similar feature. They have a 32-bit or whatever, dual 16-bit multiply accumulate. This is logic that is specially wired to have very, very low latency in doing a multiplication and an accumulation and a bunch of other features.
Okay, so if the Blackfin has these and we have them, how many do we have? How many does the Blackfin have? How fast are these things? Like, how would you compare performance of
well,
these?
if you talk about performance of the individual DSP-48, of which we have a lot. We have 120 DSP-48s on our chip, or they can be turned into 2 smaller DSPs, or they can be turned into 4 smaller DSPs, depending on how much you want to use. The same works for the Blackfin. It has 1 DSP that can also be used as 2 smaller DSPs.
So they only have 1 and we have 128?
We have 120, yeah. The difference is the Blackfin has 1 that runs at a slightly higher clock frequency, so it can do more instructions, but we have hundreds of them, so we can run at a slower clock frequency, and the performance maximums, if we were using all of this, and the whole idea behind using this device is that if we have some groundbreaking revelation of how we want to do things, we have a bunch of spare parts left over to do that in.
So is it fair to say that, like, in terms of how many max we can perform, like we're 100 times
with this
faster than,
so with
the Blackfin?
With a specific Blackfin like the BF706, they can do 800 million multiply accumulates a second. Think about that for a second. 800 million multiply accumulates a second. That is nothing to scoff at. That's pretty incredible performance. Our chip, if we used all these devices, our maximum, I think, is something like 138 billion multiply accumulates a second.
Oh my God.
Yeah, so it's it's pretty impressive. I think that, yeah, we're another order of magnitude up, but we don't have to use these just for DSP. We can use them for 100 different things. So, if we're talking apples to apples, yeah,
that's what I was asking. Yeah.
Yeah, I think we're around 120, maybe 120 Gmax, and the which is billion multiply accumulates per second, and the BF706 is at right around 800 Mmax, 800 million multiply accumulates per second.
That's incredible. All right, so now we've seen what kind of the FPGA looks like out of the box. Let's look at an area that you've designed and actually put some hardware.
Okay. Well, we talked about this thing being a big cluster of parts, and we saw what it looks like when these things are just sitting here. They're not connected. There's no wires running to anything. There are, but they're not active, so we don't even show them. But let's look at an area where we've actually done work with the FPGA. And like we talked about, we are building smaller processors inside of the logic. So let's look at one of the parts of our design that I'm actually really excited to share. One of the things you'll see in almost any of these detectors is going to be an FFT. An FFT is a DSP operation, so that allows you to look at the frequency content of a signal, right?
Yeah.
You receive a signal and you want to see what frequencies are present in it. You do an FFT, a fast Fourier transform. So an FFT is typically a very, very expensive operation. And when we say expensive, we mean it takes a lot of resources to run an FFT. So let's look at our FFT. I'll go ahead and select which of the parts. When I select this, it'll show which of these connections have been, or which of these CLBs and DSPs and all this other crazy stuff have been used to implement our FFT. So let's go ahead and highlight the parts of this that we're using for the FFT.
Wow.
Yeah. So when you look at the top of the chip, these are the areas, and you can see where they've kind of been fit together automatically. These are all the components that we're using for all the different parts of our FFT and all the other algorithms that go into that.
That's our FFT circuitry, essentially.
Yeah, that's correct. And if you zoom in on it, you can see kind of some of the stuff that we're using here.
Now, is there a way to show how these are all connected together?
Yeah, you can look at one, and we can definitely turn on the routing. Now, this is going to get a little bit weird looking, but let's actually look at the routing resources used.
I want to make. We talked about how they had roadblocks, and then we removed the roadblocks, and they're connected together.
Here we go.
Whoa.
So these are the connections. If we look way out here, now we can see the connections going between the different parts. And if we zoom in a little bit, here's those CLBs.
That's the interconnect fabric. That is so complex.
These devices, these FPGAs, are amazing with the way they distribute signals across them, especially with how tight the timing has to be on these things. They're incredible. So these are all the routing.
Thousands and thousands and thousands of connections.
That's right, yeah. Thousands of connections and then some clocks and some other stuff. But outside of that, we're also using, we can see where we've used some of the DSPs that we have on board to help do our FFT algorithm.
Can we zoom in on one of the DSPs?
Sure, let me find one. that'll be right over here. So here's one of those DSPs, and you can see how now it is connected and it has tons of wires coming out of it. These are where the different operators or all the instructions and the data comes into the DSPs.
That's incredible.
You can see where these things are kind of connected. It's pretty incredible, yeah. Very, very interesting devices. Let's see here. So when you click on one of these devices now, you can see where it's connected to the other parts of the logic. Really interesting stuff.
Wow.
Yeah, it's pretty interesting. So we have
that one DSP, those white wires, those are all the other connections that one DSP has.
Correct. Yeah, these are all the different parts of the design that this thing is wired to. And you can look at that for anything that we're using here. We can look at one of these CLBs, and we can see where these other connections are in the CLBs, and you can see how these things are wired together.
Wow.
And what's great with these things all being logic, none of these are waiting to run an instruction. Every time the clock ticks in the FPGA, of which we have dozens of clocks, each one of these is just logic elements that do their job. So they're not waiting for an instruction. There aren't instructions. Their instruction is defined by how these pieces of logic are wired together and how these lookup tables are made. So it's really interesting to see how these things are switched together and how the data flow looks through these devices.
That's pretty neat.
Yeah, it's really, really interesting stuff.
How long did it take you to become comfortable knowing, like when you're zooming around, this looks so complex to me, you seem to say, oh yeah, I'll find a DSP, and you know where to look. Is it the kind of thing where after working with it for a while, you kind of get familiar with it?
Oh, well, yeah, and it's different from device to device. So they have bigger and smaller chips that are all wired up a little bit differently, but having to kind of design these units in a way that they are reliable and they don't waste a lot of these logic elements, being more familiar with what's inside of one of these CLBs and what one of these DSPs can do, understanding how this can be routed inside lets us, when we write our hardware description language, or HDL, we can describe hardware that better uses these and is less wasteful.
Makes sense.
But a lot of it just comes from experience. Yeah, it's got a pretty steep learning curve.
Wow. Well, we really appreciate you taking the time to kind of show this to us. I mean, this is the kind of thing that, as you said, unless you find somebody who knows how to do this and lets you kind of peek in and kind of teach you and mentor you, this is just out of the realm of accessibility for most people. So I think it's really interesting to be able to have the opportunity to look at this.
Sure, and it'll be definitely interesting to look at this a little bit later when we have even more of this stuff populated. Because one of the things
I'm curious to see, like 5 years down the road, 6 years down the road, what does this look like?
One of the things to keep in mind too is that we look at this, oh man, we're two-thirds of the way spent. But if you look at one of these areas where we're using these, we're actually only using most of this stuff, even in this area, very lightly. If we look at the utilization, I mean, even in these areas where we have a lot of stuff going on,
still a lot of free space.
Yeah, there's still a lot of free space.
And some stuff like the FFT, like that's a one-time thing. Like we're always going to use FFTs.
Oh yeah.
So we've already implemented the majority of the logic that we need in here to get to where we are. So everything else is kind of just future-proofness.
Sure. We've basically, when we designed this, especially in the early stages, we did things intentionally inefficient and bigger than they needed to be, so that we were basically overspending on the stuff that we knew we had to have, and double and triple checking that we weren't going to run out of room before we got our job done. And I think we've definitely done a good job of that. Now we're starting to actually bring things down to scale, and I mean, we can look at it. We can actually look at our whole CPU system as well. So if we look at our CPU system, which is admittedly wasteful at this point, we can highlight those cells, and now we can see our CPU is taking up a whole different spot of the logic. So it's very interesting.
It's interesting to me too how when I try to conceptualize running like one CPU, an AGC thing, a DSP slice, I always thought that they would be kind of neatly separated. But it's interesting how the interconnections kind of talk all over each other. Some CLBs for the CPU are mixed in right next to ones that are being used for the FFT.
Right, and
that's not how I would think of it. I would think of it as separate blocks. Nice little neat things.
But realistically, the way that these things are, the reason that the CLB is here instead of over here, might because the other parts that it has to talk to, these things talk to,
They talk to each other, yeah.
Right. They need to make sure that we have paths that of all the
smart
millions of
routing
connections in there, right? That they're routed efficiently so that the timing works out right. So that's really the beauty of what the software does, is figures out where to put these things. It's called place and route, and the place and route algorithms are just fascinating for figuring out of all the places you could put one of these blocks, why here.
Cool. Awesome. Well, I hope you guys enjoyed this. As I said, I know it's technical, but I just frankly even just like looking at it, I think it's really cool to see. So I hope you guys enjoyed it. Hope you learned something, and we'll be with you next week. Take care, everyone.
Take care.